First generation, traditional electroplating chromium anode manufacturing has been using various metals such as lead antimony or lead tin antimony for casting for many years. The microstructure inside is loose, which is prone to defects such as cold shuts, casting nodules, shrinkage holes, and oxide inclusions, resulting in greater resistance during the movement of ions in production, thereby reducing the quality of the coating. However, the generation of high resistance not only leads to a decrease in production quality, but also generates high heat, resulting in an increase in electricity costs. As is well known, the looseness of the structure and the entry of impurities can lead to the violent erosion of weak areas by chromic acid, so the corrosion resistance of the cast anode is very low. Due to the low melting point of lead metal or lead tin metal, the lead tin alloy will gradually separate from the copper hook on the anode under the action of thermal energy, ultimately leading to the scrapping of the anode. So the service life of ordinary lead plates is generally about 1 year. Second generation, based on the casting manufacturing process, rolling manufacturing technology is used to achieve a certain level of surface smoothness. However, the structure inside the surface cannot be changed, causing the plating solution to penetrate into the interior and cause corrosion after consuming the surface. Generally, this can increase the service life by about 6 months. Third generation, after summarizing years of experience, we use high-density extrusion molding technology, 1,000-ton extruder extrusion, for chrome-plated anodes. By using high-quality lead tin raw materials, purity greater than or equal to 99.9%, adjusting the proportion of lead tin content 3 to 10%, antimony content 2-5%, and silver content 0.5-1%, and optimizing the structure of the anode, and using high-pressure extrusion molding technology. The density of the metallographic structure has been greatly improved and the conductivity has been greatly enhanced, thereby reducing metal pollution to the plating solution, improving the dispersion ability of the plating solution, and reducing impurities in the plating solution. The surface quality of the chrome plating layer has been significantly improved. We have also optimized the shape of the hook, maximizing the contact area between the hook and the conductive rod, conductive strip, reducing resistance, and thus improving conductivity efficiency. This greatly improves the anode's lifespan and conductivity, with a service life of 3 years or even more than 5 years for products with high tin content. The conductivity has generally increased by about 30%. The reasonable use of lead-tin antimony alloy extrusion-formed chromium plating anode in chromium plating can achieve a service life of 3 to 5 years or even longer, saving about 30% of electricity, and making fundamental improvements in environmental protection. The use and maintenance of anodes. The new anode is best equipped with a charged tank, and a dark brown layer of PbO, L5J will quickly form on the surface of the anode. Dark brown PbO, L5J is a normal covering layer that can conduct electricity and protect the anode surface. It is difficult to generate a yellow lead chromate film with poor conductivity when it is corroded by chromic acid. In the absence of electricity, the lead alloy anode in the chromium plating solution forms a yellow lead chromate, PbCrO, film with poor conductivity on its surface due to corrosion by chromic acid, which increases the slot voltage and even causes the anode to become non-conductive, seriously affecting the quality of the workpiece coating. Therefore, when not in production, the anode should be promptly lifted out, washed clean, and immersed in a clean water tank.